In the previous video, we talked about vector spaces, uh, and now we are going to talk about subspaces. Actually, in machine learning, we are not much interested in vector spaces, uh, but we are most interested in subspaces. Why? Because we already know that we are actually working in a vector space. The only problem lies with this that whatever problem is in our hand, whether that lies in the entire vector space, whether it is only filling the a part of it, or maybe how much big part it is actually covering. Does it follows the similar rules as that of the vector space? Is it still a vector space even if it is covering only the small portion of the entire vector space? So these are the questions that we are interested in. How much big that entire space is, which this particular problem's solution are actually covering. So with that idea, those questions can be answered with the help of subspaces, with the study of subspaces, and that's why we are interested in subspaces more than vector spaces, because whenever we are working in the problem, in a particular problem, we are generally in vector spaces itself, so that is not a big problem for us. So let us see what is a vector subspace. So let us suppose that you have a vector space V. So this is your vector space, and you have another thing, this, which has the same operations, and the field is exactly same as that of real numbers, so both of them has the field to be same, but the only difference is that the set of vectors in V is capital N, while set of vectors in U is n1. Now n1, if n1 is a subset of n and U follows all the properties of being vector space, then U is called as subspace of V. What essentially is the differences? Only in the set of vectors. So initially you have a big set of vectors, now you have a smaller set of vectors, and you still want it to follow all the properties that we have stated above in the vector spaces. So if you go through all the properties and try to find out how many properties are inherited, because n1 is a subset of n, and since all other things are exactly same, so what are the properties that are inherited and what are the properties that we have to check, that we have to identify whether they are still there or not. So those properties are particular to a subset, so whether they are still there or not, it is the property of that n1 set. It is not the property of the n set n, because those properties cannot be inherited. So we have to find out what are those properties. The properties which are inherited is like distributive property, associative property. They are definitely get inherited. If you talk about a scalar identity, that will be inherited because the set of scalars is exactly same as the previous one. We have not changed that. But there are other properties such as closure property. So as we have said already, n plus should be in abelian group. So now whether the addition of the vectors that are given, because set of vectors has been changed, whether this is closed over addition or not is a question. So when we identify, we find that if we are able to say that uh, scalar multiplication is closed, so if you take a scalar value and you take any element from n1, then the scalar multiplication between these two should still lie in n1 only, not n, n1. So because of n1, it should be in n also, no problem, but it should be in n1. Similarly, the vector addition should also be closed. So if you take any two vectors, you add them up, then the addition of these two vectors should remain in n1. So be precise, it's n1. So that's how so that's the crux of identifying whether a particular thing is a subspace or not. So we are just trying to figure it out, that whether a particular algebraic structure that we have been given, whether that is closed over scalar multiplication, whether it is closed over vector addition or not. Once we are done with that, we understand that it is a subspace. Let us do some example, one particular example for this particular understanding. So you can see this particular question. It's actually, if you collect all those points which are lying on x is equals to 2y, these are referring, this particular set is referring to this green line is referring to that set. So x is equals to 2y, all the points on x is equals to 2y are referring to this. And since in the earlier video we already said that if you take R2 or Rn, in fact, then it's a vector space. So if you take a set of vectors to be Rn and set of scalars to be real numbers, and addition and scalar multiplication is defined as usual, then it remains a vector space. So the you can see that all the vectors x and y, they are subset of R2, they are element of R2, and thereby this particular subset is also in, is an element of R2. So it's a subset of R2, in fact. So if it's a subset of R2, we can actually try to understand whether, if I say that it is n1 with normal plus and multiplication with the field to be real numbers, does this also be a vector space or not? So we want to know that. Okay, so let's go ahead with this problem. So while going to this, for this problem, first we check whether the set n1 is empty or not, because if it is empty, we cannot say that it is a vector space. You can see that in the definition of vector spaces as well, we have written that the set of vectors should not be empty. So first of all, we need to identify whether n1 is empty or not. So since c is an scalar, c is a real value, and c can be having a value 0, right? So if you say x is equals to c and y is equals to c, so at least 0 0 is in n1. So you can understand that there is at least one element in n1. Okay, now we want to see whether addition is closed over n1 or not. So let us take two two vectors x1 and x2, such that x1 is defined by 2c1 comma c1, and x2 is defined, x1 is defined to be this and x2 is defined to be this, for some c2 c1 c2 in real numbers, because that's the definition of n1. So they must be the part of n1, right? Now if you do x1 plus x2, you have to add them component wise. So you get this idea. Since 2 is a real number, c1 is a real number, and the multiplication in real numbers is distributive over addition of two real numbers. So we can write in this format, right? Now addition of two real values, c1 plus c2, is also a real value. So let us suppose that it is some c or something, some different constant. So with the definition of n1, which says that it contains all those points which can be written as 2c comma c, right? So you can see here, this particular this particular thing tells that I can still am able to write as 2c comma c. So that's how I can say, okay, if you take arbitrarily any two vectors in n1, then addition of these two vectors will remain in n1, and that's how we say that n1 is closed over vector addition. Now we need to prove whether the vector addition, whether the scalar multiplication is also closed or not. So let us see that. So you take any element x in n1. Now since it is an element of n1, it should follow the property, membership property, and that's how it can be written in this format. Now if it is written in this format, now you take any scalar value d and you multiply d with this scalar multiply with this one. Okay, once we are able to write that, we get this, because the scalar multiplication means this one. So you, what you do, you multiply separately with the all the components. So 2cd comma cd, which is again cd, because c and d both of them are real numbers, so c times d is also a real number. And since it is a real number, you can say again you have a 2e. So if you assume that c comma c in multiply d is e, then 2e in comma e is also follows the property, membership property of n1, and hence is a member of n1. So again we can say that scalar multiplication is also closed over n1. Now all other properties of being vector space is fulfilled, because n1 is a subset of R2. As I said, like associative property, distributive property, other property like existence of identity in the scalar set, they are inherited. They are coming from the definition because of subspace, because it's a subset, already a subset of the vector space, so it is already inherited. So in the now we are going to in the next few videos, we are going to study these subspaces, how these subspaces actually behave. We will have a lot of understanding about these subspaces, so that um, we can generally understand our input space of machine learning data sets. So where it comes, like, because every machine learning problem has a data set, and each data set has a number of samples. Every sample contains a number of attributes, which is generally a real number or can be converted into a real number. Now these real numbers actually, let us suppose, if you are saying that the attributes are fixed, let's say n, then bingo, you are in Rn. Now you can think about, okay, it could be a vector space. Now we are interested in, okay, does all these samples lie in a subspace? Does all these samples uh, fills up the complete space, or they fills the some portion of the main space? So those are the questions that we are trying to answer in machine learning problems. So with this idea, in the next videos we are going to study more about subspaces. Thank you.